might not be practically implemented in the industrial
like why wasn't it built, right?
Yeah.
I don't know. One of my criticisms was that.
Hi guys.
Hey, good night.
Hey.
Yeah, keep having conversation. It's all fine. We're still gonna wait the usual 10 minutes before we start.
Okay. So like one of my criticisms was that, I don't know if it's right or not, but it's they're trying to like execute types of workloads that are like very different, right?
Yeah.
Like the demorph and smorph, right? Like in demorph, I argue that workloads will become more specialized. Like there will be massively parallel workloads, right? So for example, demorph uses the A-frames speculatively, right? There's a lot of A-frames. The ones that aren't used are going to be executed. The code will be speculatively executed on them, instructions, right? And so I argued that, and so that instruction window, right, is also used in smorph to unroll the loops, right?
Yeah.
So I argued that, and they show the graphs themselves. The larger the instruction window, the more speculation there will be, and on misprediction, it's all gone, right? It's all flushed. And so, at the same time, smorph benefits from a large number of A-frames, right? So the S-frame and D-frame are kind of at odds with each other, so to speak. When there's large number of A-frames, there will be speculation and potentially wasted cycles, right? At the same time, if there's small number of A-frames, they won't be able to unroll loops as much, so like there'll be more pressure on instruction cache, I guess. I also argued that workloads would become more specialized. I also argued within one workload there's serial portions and parallel portions, right? And I don't think trips is meant to reconfigure itself like on the fly while executing a single application, right?
Yeah,
so even though
we're talking about that, so like
Sir?
they don't. Alex and I were talking about that. So he brought up the fact that there's no, like, they don't talk about how long it takes to like switch. So the overhead on that.
right, yeah.
Yeah, because like they leave it up in the paper for grabs saying that, okay, like it depends on you how you want to like switch between them. So like it might be up to the compiler or up to the programmer. But like if you're not talking about the overhead on how it takes to switch, then like, if it's really high overhead, then it's prohibitive in some cases.
Yeah, that's exactly what I wrote. Overhead can be prohibitive, and then you're not going to switch on the fly. And if you're not going to switch on the fly, then you're going to suffer to an extent from the same problems that they claim the general compute suffers, right? Underutilization or long latency for some of them. I also argued that the better way to increase hardware utilization is probably virtualizing it and putting many applications, like many workloads on the processor, thus filling up all the execution context and so on and so forth. And I think that's the way it's been going, right? It's virtualization. And then yeah, Alex.
So I assume you guys receive your grades for the first review, right? And you also get some feedback on it. So I think I told Steve to be very generous in the first review. So I'm going to talk towards the end of the lecture about, what are the typical mistakes were made there. We try not to be harsh on the first one. So if you are among the few people that got somewhat of a lower score than the average, then please try to address TA's feedback. If it's not clear, contact the TA about it. Okay? And today we're going to talk about memory hierarchy and caches. One of the first lecture. Most of the material I'm going to cover is going to be dedicated either to memory systems or to accelerators. And I guess soon after you guys figure out your projects and your groups, then I will open a schedule for your presentations on the related work. I'll talk about this in the future lectures. Also, I noticed there were several posts on Piazza about people looking for partners. If you still didn't figure out a partner, or if you're not sure about what to do for your project, you can stay at the end of this class. I'll post a link because this video is recorded, so we can use another, a Zoom link where without a recording, you can talk with me one-on-one, and I'll talk with you about the project and try to brainstorm a little bit about what you want to do. If you already know what you're doing, that you don't need to attend this. And for people that still feel lost, especially for undergrad students that don't know much about research. Okay, I think we really have everyone based on the number of review submissions we have, so we should just start, I guess. Okay, so welcome back. Today we're going to talk about memory hierarchy and caches. So I think once before we get these questions about what we're supposed to review, so I put it in the first slide. For this week, you're going to get to review one of my papers. I promise that's the only one time we're going to review one of my papers, so I'm not going to be too biased. But I think this paper is quite relevant to today's conversation. So we're going to talk a lot today about caches, replacement, and capacity of caches. So this is one of the creative ways to get extra capacity in the caches. Again, from previous iterations of this course, students usually said that was a relatively easy paper to read and understand, so I keep it here, okay? Okay, project proposal deadline, just a reminder, October 1st, right? For the proposal deadline, again, we don't expect a huge proposal from you. We expect a couple of pages, right? That would summarize what you want to do, what the milestone, what your vision, and things can change, obviously, right? So by now you should be working on forming a team and working together on that. So remember, that's a collective project. Okay, any questions about project proposal or any logistics stuff related to the course?
When did you say you would have that meeting to help us with the topics?
With the topics, so every time after the presentation is over, like in the class, if there are some people willing to meet, right? I will.
Oh, so you mean just like after
the class? Yeah.
Okay.
Right after the class. Okay. Any questions? Okay, but as I said, I don't expect everyone to show up because then it's going to be a long meeting. So it's mostly if you're not sure, then you come, right, and what to do. I hope some of you already know what you're doing. Okay, so today we're going to talk, and for the next few lectures, we're going to talk about memory. And specifically, we're going to talk about it from the very high up level, from the programmer's view, all the way to the core implementations of it. So from the programmer's view, the memory view is very simplistic. I had the store instructions that goes and stores something into this memory, and I don't really care how it's organized. I know that after I had a store, eventually it will be written there within a certain time frame. And then when I load something from the memory, I'm going to, based on certain address, I will get results back. That's programmer's view. So it was not always like that. Obviously, for a long time, until virtual memory was proposed, people manipulate with physical memory and has to deal with all the complexity of dealing with physical memory. Luckily, those things, are not true anymore for quite some time, although some people still try to revise it and suggest we should get rid of virtual memory because of too high of an overhead. By the way, the usual question, if you can turn on your camera at least sometimes, that would be very helpful. Thank you. So at least part-time, so I can see whether I'm too fast or too slow, or if you're puzzled. Okay, so from the programmer's view, when they use virtual memory, memory is pretty much infinite, right? You can keep writing into memory, although physically it's not, so you're going to be penalized eventually. But reality, as I said, physical memory is much smaller than the programmer assumes. And so the system, which is system software, hardware, had to cooperatively figure out how to map those virtual memory addresses, potentially infinite, to the limited physical memory, right? The system automatically manages the physical memory and transparently to the programmer. The beauty of this abstraction is the programmer does not need to know the physical size of memory nor manage it. If you're going to read the stories about these old computers and how they were managed, people literally were memorizing certain address spaces where they need to put certain things. So you can imagine that complicates both, writing complicated programs. So essentially, they didn't write too of a complicated program back then, really, from the design standpoint. They were complicated from the mathematical or physical standpoint, but not from design standpoint. And yeah, there's like bugs and there's things that are just were impossible to fix or very difficult to fix, let's put it this way. A small physical memory can appear as a huge one to the programmer, so life is easier to the programmer. So this is why virtual memory was introduced and still used heavily. But it definitely has its downside. It complicates system software and architecture. And if you ever work across the full system stack, you will see how many complications comes from the fact that we had virtual memory. And this is a classical example of the programmer versus microarchitect trade-off. So it's classical from the sense is that the microarchitect, want as the minimal guarantees as possible and trying to push all the work to the programmer, but programmer going to be pushed back and said, no, I'm not going to do that. And you always look for a compromise between the two. So then you figure out who's responsible for what. So for example, in virtual memory, some responsibilities goes to the operating system, right? Okay, so we're going to talk a lot in this class about the physical memory system. So essentially, you need a larger level of storage to measure a small amount of physical memory automatically. And we always assume that a physical memory has some backend store, something like disk. It doesn't have to be, hard drive, but it's something that is essentially persistent. This idea of memory not being persistent is questioned right now with non-volatile memory, but still overall, the most usual case, we assume that the memory is volatile and it needs some backup storage. It's not, again, written in stone. Remember, people propose single level store, where essentially there is no like disk and memory. Everything is just memory and memory is persistent. And it's an interesting direction of research, but this is not something we're going to talk in today's lecture. We're going to talk about more conventional system. So we'll first start with the physical memory system. So for now, please ignore the virtual to physical indirection. And I would say even not for now, I don't think I'm going to have time to talk about virtual memory and related optimizations. So most of the conversations we're going to have is going to be about physical memory, the way it's really physically implemented, okay? Okay, so we'll talk about the ideal scenarios first. So if you build a compute engine, so ideally, like when you look at the stages that you had instructions, you had pipeline that executes those instructions, and those instructions needs data to execute. This is like a classical von Neumann model. And the ideal case for us is no pipeline stall, perfect data flow, like register memory dependencies barely exist, zero cycle interconnects, so there's no like delays of operand communications, always enough functional units, zero latency compute. Under those assumptions, you can get certain performance that's just literally dictated by how good is your code, right? And how well compile optimize it. Reality is, of course, you don't gonna add all this idealism. So we're gonna talk about how these different things break in different places and how it affects the performance. From the instruction supply part, you want zero access latency, infinite capacity, zero cost, perfect control flow. So essentially perfect control flow means like your branch prediction is always 100% accurate. Obviously you want, iCache being, infinite in space and things like that. From data supply, very similar things. Zero latency access, infinite capacity, infinite bandwidth, and zero cost. Data supply has bandwidth because you tend to read way more bandwidth, way more data than instruction. Bandwidth is relatively small compared to data bandwidth. Okay, so we'll talk about the memory hierarchy that's supposed to help to bring us a little bit closer to this ideal scenario. So first of all, why there is such a big emphasis in this course in memory, I keep bringing this up again and again. It's not my personal choice. It's really dictated by what is dominant. So if you look at the chip and you're gonna look at what is taken by the memory hierarchy. So you're gonna see here there are cores. By the way, this course also had some L1D caches and L1 instruction caches. But still, you see the relative area of these 4 cores, and then you had L2 caches here, right? Then you had shared L2, and there is DRAM memory controller that sits, in this case, on chip, and there is DRAM interface, right? Sorry, it's off. It's on there on the board, but it's not on the chip itself. It's located here, and then there's a DRAM interface, and there's obviously DRAM banks here. So you can kind of see already by where the area goes and where the silicon goes and the power and the cost. Memory is a big deal, right? It consumes a huge part of the total area, power, and cost budget. And as I said several times, this DRAM banks, which we're going to talk a lot, actually the most expensive part in most of the cloud nodes right now. Any questions so far? This is more like a repetition and basics for people who take computer architecture classes, but I want to make sure that everyone understands the motivation and the basics and why you should listen for me for the next few lectures and care about memory.
Hi, Gennady, I have a question.
Yes.
Usually, we have the cool down to the temperature of the CPU is usually very high, but the temperature of the memory is not so high. And why? So why is the DRAM cost most of the memory, the electricity?
Yeah, it's a good question. Although I want to start with the fact that the temperature is quite unrelated here. So there is a manufacturing cost and it has nothing to do with the temperature. By the way, you can make DRAM really hot and it can break, like we did it. Like we put essentially FPGA-driven board with a lot of DIMMs onto the temperature chamber, and if under certain conditions you can make DRAM to starts to warm up and had issues. So okay, so but to briefly answer your question why DRAM is so expensive, right? It's mostly the manufacturing cost and the density, right? So first of all, it's not like let's say Samsung is really getting they're not selling DRAM unreasonably expensive. If you look at their margins, this is nothing compared to say GPU margins. So like NVIDIA's or AMD's earning way more money from selling their GPUs than say Samsung or Micron from memory. Because the manufacturing cost, the density, and the supply you need is that making it expensive, right? We are going to talk in this course about why DRAM is considered to be still slow and why you need so much memory. I think fundamentally your workload your applications require more and more memory capacity, and that makes it expensive. And for a long time, another reason why I believe cores are simpler, not simpler, but cheaper, in the sense we were able to scale them for a long time, almost exponentially, right? With the transistors count, and memory never scaled that well. So it was always lagging behind. It started when DRAM first appeared with something like 20 cycles or 30 cycles, and now we're talking about 100 cycles. So DRAM lags behind, and the problem is that it's very hard to manufacture as having high capacity and also high memory bandwidth and low cost all at the same time. So like there are a lot of memory alternatives to DRAM that can be faster or cheaper, but they cannot satisfy all the requirements. So high capacity, high density. So there's the one that has higher bandwidth, lower cost, but don't give the enough capacity, like things like that. There is always something that breaks, that doesn't bring it. And it's very difficult to bring another technology and find it niche. So it only really happens maybe 3 times in the last 40 years. So DRAM, then after that we got SSD. So we got some technology that find a place between disk and DRAM. And another technology, essentially a non-volatile memory right now from Intel, like very recent ones. So there's really 3 technologies that find a place in real product. While Micron, I've seen their presentation, they try like 20 or 30 different technologies, and they just fail, right, at the scale. Yeah, we'll talk a lot about that, but it's not temperature related, something I want to say. This is more like a side effect of how things operate. Okay, any other questions? Okay. So as we said, ideal memory should have 0 access time or latency, infinite capacity, 0 cost, and infinite bandwidth to support multiple accesses in parallel. The problem with the ideal memory requirements is opposed to each other. So if you want bigger, it means it's slower, right? I guess it's not a surprise to everyone. If it's faster, it becomes more expensive. If it's higher, it's even more expensive. So right now, modern memories, again, I'm not going to talk as deeply about transistor and circuits here, but essentially right now, the most expensive part of memory is actually high bandwidth. So you would see that getting the one of the biggest cost drivers, and for example, in GPUs, is the high bandwidth memory they use. Like HBM, it takes a lot of power and it's super costly. So like NVIDIA used it for several generations of their GPUs, and now they're trying to switch to GDDR6. GDDR6 was not available right away, but they prefer to switch to that because high bandwidth memory is extremely expensive. Yeah, so bigger is slower. Why this happens? Because it takes longer to determine the location. Faster is more expensive because it's memory technology. So essentially, if you look very rough, there's SRAM, DRAM. In between that, I don't put it here, but there is also SSD and disk, like hard drive, and there is tape. So tape is the cheapest, obviously, right? But I mean, it doesn't have the latencies you want. By the way, I had this, I think when I took my networks class many years ago, I got this interesting question. I guess I want to challenge you guys with that question as well. So when you think about all these different technologies, specific to the problem, the solutions might not be as obvious as you think. So imagine that you would need to transfer something between, say, Toronto and Beijing, and you want to transfer as many bytes as possible, the most cost-efficient way. So what would you use? So what would be the best solution?
Tape and an airplane.
Any other options?
Does it depend on how much? How much do I want to transfer?
bring the maximum, like you want to get the highest possible bandwidth.
Is time, I'm guessing.
But there's no latency requirement.
No latency. Okay, yeah, just put everything on a big freight truck, like
a lot of tape.
Yeah, a lot of tape. Like really,
yeah.
On a ship.
Cheap.
So the problem, like if you want bandwidth, so it's not latency critical, but still it's too slow. So the best is the plane. The plane and a lot of your tapes on it. So that gives you the biggest density for space. And if you don't care about latency, that's as good as it can be. Like if you do this mental experiment and you do the math, you figure out that the trade-off might change a little bit or not. But it's not that it's not the internet that students usually think about or any of these fast transfers, right? It's using the plane stashed with the tape that gives you the best solution. This is because you drop latency. This is the example shows you how the trade-offs are important, right? Like if you add latency to the equation, your solution changes quite dramatically, right? Okay.
So just a quick question. What's the difference between SRAM and DRAM? Like
we're going to cover that in a lot of details even today.
Okay, cool.
You're going to learn it. So just be patient. And higher bandwidth is more expensive, so need more banks, more ports, high frequency, or faster technology, or all combinations of all of it. Okay, so as you just asked, the memory technology, DRAM, right? So it's called DRAM because it stands for Dynamic Random Access Memory. It consists of one capacitor that indicates their charge state, and whether the capacitor is charged or discharged indicates storage of 1 or 0. There is some, rules about when it's 0, when it's 1. I don't really care about that from the PHY perspective. It's built of one capacitor and one access transistor, and that's just a rough diagram. Here, one of the key characteristics, important characteristics of DRAM that changed a lot in how you design it, is that because it has capacitor leaks charge through the RC path over time, which means DRAM cells loses charge over time, which means to keep the information in there, you need to periodically refresh it. So the most typical DRAMs that you have right now on your laptop, probably every 64 milliseconds, they're going to do the full-blown refresh of everything, right? You can play with it, and this timing parameters can be modified. You can reduce it all the way to a second. At some point, you start to get a lot of errors. Okay, this is the important thing, the important bit you need to know about DRAM. So it's manufactured differently from their, from the gate level. And that's where its advantages and disadvantages are coming from. So another memory technology, SRAM, and again, this is not the course that's going to cover that in super high level of detail, but I'll give you a good understanding of it. So it's called static random access memory. So it uses two cross-coupled inverters to store a single bit, and feedback path enables the store value to persist in the cell. So it has 4 transistors for storage and 2 transistors to access. So it has 6 total transistors that you need to use. So you see it's persist in the cell, so you don't need to refresh it. But it's definitely more expensive to build it. So it's harder to get high density with this design. So this is there, I just demonstrated a couple of technology. We're gonna go much deeper into that. Again, you don't need to memorize these things. This is just more like giving you an overview how things are organized so you better understand the papers you read and things like that. So how is the memories organized? So there is a memory banks, and this is where you store the data in DRAM. Essentially, the best way to think about it is a 2D storage of array with all these small cells. And we have a way to read the data using rows and columns. Right? Again, the exact details we're going to cover when we're going to talk about DRAM. It's important to different optimizations in it, but the very high-level overview of it. So when you had a memory address on the left, it goes and extracts the useful information from the put it in those registers, and they had most significant bits and least significant bits. And most significant bits identified the row in which you store it. You can think about like a 4 kilobit or 8 kilobit of information stored consecutively, right? And so your address tells where that's located, and then you can read pieces of it through a column decoder, and that's lower the bits of your address. So this is specific 4 byte or 8 bytes you're trying to read. So essentially we decode raw address, we drive the word lines, right? Select bits that drive the bit lines, and then you read the entire, activate the entire row. Then we amplify the information on the raw data, then you do the decoding and read the data, send it to the output. And then we need to pre-charge bit lines again. So because DRAM, when you read the information, it loses charge, right? So you would need to recover the information that was stored there. Otherwise, it would be destructive. Again, I don't expect you to understand every little bit of details, but this is a generic flow of how you read data from something like DRAM. From SRAM, essentially the read sequence conceptually is similar, although the organization is different. So you also had an address decode in this diagram, then you drive the row selection, you select bit cells that drive certain bit lines, right? Entire row is read together again. We're going to talk later on why it's done this way. And then there is some sense amplifications and column selection happen for the data through all these muxes. And then you pre-charge all the bit lines for next read and write. And access latency are dominated mostly by step 2 and 3. Okay, so this is just very high level. Okay, and this is how you do it for, again, for DRAM. Again, I'll leave the slide here. You can look at it later on if you want to understand how it's different from SRAM. A lot of sequence of steps is pretty much similar to SRAM. So there are some specifics about DRAM here to regenerating the information on the bit line, but from their computer architecture perspective, the operation is similar. What affects us is that the reads are destructive. So if I keep reading from DRAM, I destruct the data, the chart stored there, and that's a problem. And I need to fix that over time. So here I'm saying it's tens of milliseconds, but the most typical DRAM you're going to use right now on your laptops, probably which you're using right now, is going to be around 64 milliseconds. Although we're going to talk about some problems with existing DRAM, such as Rowhammer, where there is a specific attacks you can do on DRAM. And then one of the solutions, which I believe is a very dumb solution that Apple proposed, was to increase the refresh rate. So they might refresh your stuff more frequently if you're using a Mac laptop. Any questions so far? This is just like an overview, and each of these SRAM, DRAM, we're going to have like dedicated lectures on that and caches. So I just want you to understand the slight difference in the technology and how it affects the design. I think, Mustafa, did I answer your question partially at least?
Yeah.
Okay. So what you really care about, those slides are more like if you want to refresh it for yourself. But what we care about is fundamentally DRAM is slower, right? It has a capacitor, that's why it's slower. It has much higher density. Why? Because it's only need one transistor, one capacitor cell, in contrast to SRAM that has 6 transistors in the cell. DRAM, because of its higher density, it also has a lower cost. Getting a lot of SRAM is non-trivial. For a long time, SRAM is used as a technology, it's used for registers. So if you wrote an assembly code, which I hope all of you did, the registers you use, like, EX, EBX, they're all implemented using SRAM, and so is implemented your cache, right? It happens to be a good trade-off in terms of latency versus capacity needed. But say if we're starting to think about, memory, then most of the memories is right now based on DRAM technology, right? Because you need much higher capacity, right? There are companies right now that are trying to build chips with a lot of SRAM, and those chips are not surprisingly super expensive, right? So whenever you hear that company X built a chip with 18 GB of SRAM, right? Always think about it. There's no like free lunch here, so this is an expensive technology to have. So this chip is probably going to cost like hundreds of thousands of dollars. Okay, any questions so far?
Good idea. Quick question. 2 questions actually. So how much has memory technology, and if so, how much has benefited from Moore's law, from our ability to exponentially cram transistors in the same area? And second question, I'm older, I remember when I looked at on Amazon, memory used to be like more expensive. Now it's much cheaper. How did they reduce? Why did it dramatically drop in cost?
We're going to have this graph at some point, but you would see that the memory capacity and density of memory never keep up with the compute, right? So for a long time, where say compute grew up 2x every 18 months, memory at the very best improved 2x in 3 years. And then it was always lagging behind, which was keep increasing the latency. Different aspects of memory grow differently. So at some point, I'm going to have this graph where I'm going to show latency trend, bandwidth, and density. And each of them lag behind, but just differently, depending on the technology they develop. So the short answer, yes, they also benefit, but not as much as compute. So it turns out to be built-in memory is more built-in memory that satisfies the requirements we want. It's harder than manufacturing the chip itself. So built-in chip is difficult, but the cells for chip or the technology that you can shrink was harder. And one of their, one of the issues with DRAM that is the technology is different. So DRAM is manufactured from capacitor and transistor, so it's not matching the technology used for compute and SRAM. So there's a big barrier there. So when people propose ideas like compute in memory, one of the first fundamental barrier was how I'm gonna, connect these two different technologies, manufacturing process in each other. And I think Micron did a prototype and show you can add an extra 3 layers of some material and connect things properly so you can make compute in memory actually. So it's not a hypothesis, it can be done. Right now there are companies that do manufacture that stuff, given startups. But for a long time, people hypothesized about it, but it was not easy. Yeah. So there's not like a single simple answer. People keep trying a lot of things. If you look at Micron slides, whatever they present, they like try zillions of different technologies, and it's just trade-offs. And I talked with you 3 about 4 different metrics. They had like 7, 8 different metrics in Micron that we don't even think about different resistance, drift, and all the other side effects that we're not familiar with physics that we don't think about. Okay, so another thing as computer architect, because we don't need to understand all the details. Oh, Mustafa has a question.
Yeah, sorry, you said before that like SRAM was used for cache and stuff. Is that still the case, or do we have more mature technology?
Right now, I'll talk about most of the caches are still done using SRAM technology. So the majority, so essentially, the majority of caches right now, like L1 cache, L2 cache, L3 cache, are all done using SRAM. But there are very deep, we're going to talk about memory hierarchies today. There are machines that built specifically by IBM, like huge mainframes, actually had 5 layers of caches. So as you want to really big cache, right, something on the orders of gigabytes, then you can't really have it using SRAM technology. So they start to use some NVM or other technologies to do it. So it still operates as cache. The one you need to think properly about it, whether it's a cache or memory, it's not about technology, it's about the way it's used, right? But different technology might be suitable to achieve a good trade-offs. Did I answer your question, Mustafa?
Yes, thank you.
Pavel?
Is there anything between DRAM and SRAM?
Not in your existing system, right?
Wouldn't something like Optane fit in there, like the NVM? I think that's.
Optane NVM would be from the other side. It would be in between DRAM and SSD.
Oh yeah, okay, my bad. Yeah.
So the best you can do with Optane is make it closer to DRAM or use it as memory, but never closer. It has higher latency than DRAM, and a lot of other issues we're not going to discuss right now, right? But it's more like, ideally you want something like NVM to replace everything, SSD and memory, but it has a lot of downsides to it. It's not easy. Okay, coming back to the material, but please keep asking questions. So DRAM fundamentally requires refresh. So it's power, performance, circuitry needed for that, right? It's very costly. Manufacturing requires putting capacity and logic together, which means that the people who manufacture CPUs not necessarily know how to manufacture DRAM. That's 2 different technologies, right? So Intel, who manufactured a lot of silicon, still buys all the memory from Micron or Samsung, right? For SRAM, you see all the opposite characteristics. So manufacturing compatible with logic processes, they're doing compute in SRAM and connected it closer to compute is easy. That's why SRAM is used for both registers and caches. Okay, so here I'm going to show some data. The data is old, from 2011, but it gives you a sense on the delta difference between different technologies. So when I said bigger is slower, then SRAM used for registers in CPU, we're talking about hundreds of bytes, maybe about a kilobyte. And that, the latency to access that even 10 years ago was sub-nanosecond. So that's how fast it can be. As you ask for more and more SRAM, and I'll show you later why, you're going to get kilobytes or megabytes of it. Right now, we can get even gigabytes apparently, thanks to some companies, but that's going to be nanosecond granularity. DRAM is in gigabytes, and that's 50 nanosecond on that order. Let's put it this way. And hard disk, you can give terabytes, and you get milliseconds, 10 milliseconds. So the reasons why NVM, sorry, not NVM, even SSD appeared, you see a big gap between DRAM and hard disk, right? At some point, it starts to really become a problem. So people were looking for technology to fill in this niche, right? That's how SSD finds its place. Okay, faster is more expensive again. This is all numbers, but roughly speaking, it's like a SRAM was having $10 per megabyte, right? DRAM was $1 per megabyte, and hard disk was $1 per gigabyte. So you see where the difference comes in terms of cost. And that's what's driving technology. When you do work on research, you frequently talk about other metrics, performance, utilization, and things like that. Just to be honest and to be pragmatic, when it comes back to industry, everything is driven by the cost, right? So the cost of manufacturing and say performance per dollar, that's really the primary metric. It's hard to measure. So researchers tend to stay away from these metrics for obvious reasons, but it is the real metric that drives a lot of these things. And when we work in computer architecture fields or system fields, we should also remember that to make sure that our papers are realistic. Okay, so other technologies are getting their place. So flash memory, PC RAM, MRAM, resistive memories, not a lot of them mature. Like Intel's NVM is here, but again, we can only hypothesize which technology it uses. I don't think it was ever released, right? So we don't really know. We can, obviously there were people that open it up and try to load, but Intel didn't make any official releases on what it is. I personally believe it's some forms of phase change memories. I don't have time to talk about it in my class, but if you look at some lectures from other universities, you can, read about phase change memory. So it's essentially from a very high level, instead of using capacitor to store information, what you do, you had a material to which you can apply the charge, and it's going to take, depending on how you apply the charge, quickly or slowly, it may become amorphous or it might become solid. And that's essentially the building block of your memory. So the state of matter of that material says whether it's 0 or 1, right? That's obviously non-volatile, right? It doesn't leak charge because charge is not involved. There's no capacitor. But there are tons of other problems such as reliability and things crack if you're gonna flip it a lot of times, right? But that, I believe, is the building block behind what Intel did, because before they ship it, a lot of research from their groups was coming working on phase change memories. So you kind of get a feeling where they're coming from. Okay, so if you look at more modern data, I think I collected it either 1 year ago or 2 years ago. So just to update the slide. So SRAM is about $5,000. Like I converted everything in one metric in gigabytes, so it would be easier for you to compare. So essentially, again, so it's not state of the art. It's not like collected this year, but it's probably 2 years ago. So SRAM is $5,000 per gigabyte. DRAM is about $100 per gigabyte. You see 50x difference between SRAM and DRAM in terms of cost. And SSD is 50 cents per GB. So if you want to make an impact, this is the deltas you need to look for, right? So it's like the people won't buy 10% changes. People need like orders of magnitude speed ups. Hard disk is 0.04 per gigabyte, right? And NVDIMM right now, that's the non-volatile DIMMs that Intel is selling, is about $10 per gigabyte. So as you can see, if you compare it with SSD, this is definitely still more expensive than SSD. It's still cheaper than DRAM, and that's why about 10x. This is why it makes a lot of people in cloud very excited about NVM, because they can drop the cost of DRAM by about 10x. But there are tons of challenges with using NVDIMM, right? So it's not like you just took your DRAM on and plug in NVDIMMs, right? It's not going to work like that. You actually have to rewrite your applications, unfortunately, to use this technology as memory. Okay, so obviously, since we had these trade-offs, very quickly people realized that we'll probably need a memory hierarchy, right, to benefit from having all this different technology. So if we want both fast and large, and we cannot achieve one with a single technology. So what we want to do, we want to have multiple levels of storage progressively bigger and slower as you get further away from the processor. And we want to ensure that most of the data the processor needs, we keep in the faster levels. So the trick is then to create an illusion that most of the thing you need is kind of very fast, even though they're not really stored in the fast memory. So essentially, this is a very high-level figure that describes that: fast but small, big but slow, right? And that's a trade-off. So essentially what we do here is we try to get layers in between, and there is some backing up storage that protects us, something like hard drive or tape. And essentially what we see right now, this fundamental trade-off in computer architecture is used for, since the cache was invented, essentially since the 70s, right? So you had CPUs, register files, you had caches, potentially multiple different levels of caches, and you had main memory and hard disk, and potentially extra layers, multiple layers of caches, potentially something in between main memory and hard disk, like non-volatile memory, but that's what you have. But this is the fundamental reasons why the memory hierarchy exists. So one way to think about how we can utilize that faster but smaller unit is by utilizing the phenomenon that calls locality. Remember, if the data would be accessed would be completely random, that small memory but faster won't really help us much, because we're always going to be reading something from that we cannot fit. But luckily to us, the phenomenon of locality exists. It happens that the way we write programs as programmers fundamentally has locality, and there are two main types of locality people consider. One is temporal locality. So if you just did something, it is very likely you will do the same thing again soon, right? Since you're here today, for example, there is a good chance you will be here again at the same time next week, right? That's a temporal locality, right? If you think about spatial locality, I usually make this joke when the people actually sitting in the room, and it works very well. I guess right now everything is virtual, so it's not as funny anymore. But you would see that, right? If you look at how people sit in the room, if you sit in one particular place, there is always a tendency that students sit in the same place in the class every time they come, even though it doesn't really matter when they come, early or late. They always prefer to pick the same place they pick from the beginning. That's a spatial locality. So I can predict rather where you sit.
It works even better now because we're all still always likely to be in our house during the lecture. So if anything, it works better.
Yeah, it's true, but it doesn't sound as funny when I give it in a third lecture and literally every single person in the room sits in exactly the same position they pick in their first class. And you kind of even can memorize roughly who sits where, because it's relatively small class. I never had more like 15, 16 people in this class, right? So it's kind of funny that that's both temporal and spatial locality is not only for compute, but actually for real life. Okay. So memory locality. So how do we use it? So a typical program has a lot of locality in memory references. Because typical programs are composed of loops, right? And that's a fundamental thing. It's not made up. So temporal locality benefits from it because program tends to reference the same memory locations many times and all within the small window of time. And the spatial locality, a program tends to reference a cluster of memory locations, at a time, right? So if you access something in the memory, there is high likelihood that the next few 8 bytes or the previous 8 bytes would be an interest for you as well. So most notable examples in the instruction memory reference, like we tend to read the instruction streams sequentially, right? Yes, occasionally we have branches, right? But still we tend to access a lot of things sequentially. And then a lot of data, when we work on big, massive, data arrays, we like to store them in certain data structures like arrays or linked list, and there is locality because of that as well. So caching essentially exploit both types of this locality. It's one of the biggest inventions in computer architecture, invention of the cache. I don't know how many of you know who invented the cache. So there was actually an interesting debate. So there are people that a person that accepted to be the inventor of the cache I think George Wilkes is his name. But IBM as a company disputed this for a long time. They were saying, you know what, we actually invented cache early, but we were so worried to release this information. So because it has given us such a big competitive advantage. So we keep it confidential. We didn't have even a patent on it, right? So we now have a patent. We didn't have any papers, but we do have it. So it was an argument back in the 80s about who has invented it. So most people agreed that the claims like that by the companies are not substantial, right? So even if they had it, but you keep it for your as a trade secret, then sorry, you cannot claim you're the first inventor, right? You have no proofs, right? So essentially, generically, it's that George Wilkes is accepted as the inventor. So by the way, if you read this paper, you're going to be quite confused because even though it has this idea, things are described way differently that we like to think about it, but still you can see the principle was there. So essentially the idea is from the temporal perspective, the data will be accessed again soon. That's the key idea. So if I access something, there's a high likelihood I'm going to access exactly the same object. And temporal principle, recently accessed data will be again accessed in the near future. This is, I cite the Wilkes early papers in 1965. That's when the idea came out. So that's what he said. The use is discussed of a fast core memory of, say, 32,000 words. Remember, back then, 32,000 words sounds like very large. As a slave to a slower core memory of, say, 1 million words, in such a way that in practical cases, the effective access time is near of that of the fast memory than of the slow memory. So you see, it's a game of illusion. You're trying to reduce locality by using a smaller set of words to create an impression that you always access everything from that fast memory, so that the effective average access memory looks like you always read pretty much from the fast memory. That's the key idea behind it. The idea about spatial locality is about storing addresses adjacent to the recent access data in an automatically managed fast memory. So this is why memory is divided into equal size blocks that we fetch them in the cache in a certain way. And essentially anticipation hypothesis here is that nearby data will be accessed soon. One question you might ask, well, I can easily write an application that can break this principle, and you're going to be absolutely correct. The thing is, the majority of the program we care about are written obeying this principle and benefit from it. So we are trying to build hardware for the common case, not for specialized case. That's why they're called general purpose CPUs, right? So spatial locality principle is essentially near data in memory will be accessed in the near future. Sequential instruction access is one example. Array traversal is another common example. So those are very common primitives. And this is what one of the first IBM machines implemented. It turns out what was funny, so that's the first paper that IBM actually published in 1968 on that. And it was interesting when the people came up with caches, like one person thought about temporal locality and IBM people actually thought about spatial locality. You can see how one people comes from a fundamental principle of the program operations. They thought about one thing, but the people who actually have to design real hardware, like IBM, they actually thought about spatial locality because that affects them a lot, right? So you see how important, if you want to actually contribute to the state of the art, kind of trying to be in both camps in some sense, right? You want to think from the first principles and always look for opportunities from understanding your user, understanding your client, like a program in this case. Well, it's also important to understand how things manufactured and built. So this is why the first cache that was implemented by IBM, that it has 64-byte block. And you might be surprised, like how many years ago was that? Like more than 50, right? We still use 64-byte blocks, right? So it means that the fundamental principles that lays behind why they selected 64 bytes are still more or less the same. It's not written in stone. You can find some GPUs these days that use 128-byte cache blocks because GPUs have slightly different architecture, or not slightly, I would say, but they figure out that for them, the optimal might shift a little bit. But I found it quite fascinating that something that like capacity of caches changed since then a lot. But the size, the granularity of the block didn't really change, right? There's some patterns on how we write applications and data and how we reuse the data that tells us if you're going to have much larger block, you waste too much, right? There's not enough spatial locality to go for larger blocks. And this is one of these interesting observations, right? And people, by the way, build caches with all these different sizes, 16, 32, but 64, that's still what you're going to probably find in your laptop right now, even after 50 years of research on the topic. Although the capacity of your cache go quite significantly up since then. Okay, any questions here? Okay, yeah, I apologize for people who took advanced computer architecture classes before as an undergrad. Probably a lot of repetitions for you, but I'm pretty sure there are people who didn't. So you're learning something new. So the best idea to think about memory hierarchy is the bookshelf analogy. You can have a book in your hand. This is your registers. You can have it on your desk. You can have it in your bookshelf. You can have boxes in your storage, you know, at home somewhere packed, and you have the boxes in your storage. So the capacity grows the further away from your hands you go, right? So that's the latency difference versus capacity difference. Okay, so adjacent books in the shelves needed around the same time. So if you categorize and organize your books well in your shelf, then you benefit from both types of locality. Okay. So caching in pipeline design. So how, I assume a lot of you at least took the computer organization classes, so you know about pipelining designs using modern CPUs. Because pipelining is so integral for chip design, caches has to be integrated with it. It's not always easy. So the thing about pipeline, the key principle is you expect that every stage of the pipeline takes one cycle. The problem is, if you're going to have caches in memory, that principle breaks, right? Because accesses from caches in memory won't take a single cycle, right? So that's one of the challenges. So the high frequency pipeline, you cannot make the cache too large because you cannot sustain that frequency. But we want a large cache and a pipeline design at the same time, so you get a trade-off, right? So you want very low latency to make your pipeline alive. So someone's want to take on this question, so why it's so critical to have one cycle latency for the pipeline, like from like what is really, what's going to happen if you don't do it? Oh,
I can try. The frequency, you won't be able to reduce frequency?
No, it's not. Like what fundamentally happens with the pipeline if one of its stages cannot sustain one cycle latency?
Like, I guess you need to rework how the CPU works, because like if you're waiting for some data to come, you need to know when to operate with that, right? So you need to know.
Generically correct, but there is a term for that. So that's what I was hoping to hear, that someone probably took computer architecture class before. So what happens is,
teach us this sort of stuff in like B58. It's been traditionally very useless. So
Jimmy, you raise your hand. Mute yourself.
I think because if there is like one instruction that you want to add, but that has a data dependency, and you want to get the data in, but you can't get it there in time for that one cycle, you need to push in an additional, either like a no-op or try to fill in some other instruction there.
Get into it. So what do you get? So if that, you're absolutely correct, that's what happens. So how's that called? So what do you get?
Like a bubble?
Yeah,
I think it's called a bubble.
Bubbles. So you essentially you waste cycles in your pipeline. So the whole point of pipelining dies if you had large cycles. So the pipeline, like think about the factory, there is a pipeline there. If you had, you know, one thing that's waiting for something, everything else stalls, right? The pipeline stalls. So the factory is only efficient if you keep up shipping every single stage at the same frequency, right? As soon as it's not, it cannot keep up with one cycle, and it's broken, right? So we want large cache, but large means slow, right? And we won't have a pipeline design not being broken because it's critical for our performance, you know, of the chip. So the idea we handle that is building a cache hierarchy. So L1 cache, L2 cache, L3. As I said, I've seen some IBM designs crazy, in my opinion, with 5 levels of caches. This is how deep can people go. Jimmy?
There's one more question I wanted to ask you about that issue. So let's say the top level of your cache hierarchy does actually have the low enough latency to match with the pipeline cycles. But let's say you get a cache miss and you have to go then retrieve from a lower level of the cache,
yes,
and that is too slow. Would that not introduce bubbles? Like,
You're absolutely correct. It will, and there would be a mitigation techniques to deal with that. But the key point is that you hope when we will the multi-level hierarchy that say 90, 95, 99% of accesses into the cache would hit the L1, which means
Okay.
there's only 1, 5, or like 10% of the worst case accesses goes to the L2 and further down. So the best way to think about it is a filter. There are multiple layers of filtering. So even though sometimes you have to go to L2 and instead of 3 cycles, you're going to spend 20 cycles. And, 1% of the time, maybe go to main memory and you have to pay 100 cycles. But the average latency, that's what you care about, is still, low. So you don't really pay 100. We're going to make an example on one of their Pentium machines. So you're going to see how it works on the concrete examples. But that's one of the main principles. Okay.
So can I?
Yeah.
Quick question. So then the processor would attempt to schedule hopefully another instruction, right? Potentially from a different thread, right?
I'm talking about other ways to mitigate latencies, like a multi-thread. In the classical processor, has just one stream of instructions, right?
Right.
Like I guess that's also where like the out of order execution comes in.
Yeah, we are not talking about out of order, but even there, it's like the thing is, if you had a dependency, right? Even if out of order, what if you don't have another stream or you don't have another instruction that would be independent, right? If you had one critical instruction, blocks everything, even an out of order engine. Out of order engine hopes to find something that can be done in parallel, but you've had one. Even out of order struggles with the pipeline bubbles. And remember, pipelines, CPUs right now, actually, they don't have like 5-stage pipeline that you probably learn in computer organization class. They actually have like 20-something stages. So this is why branch predictions of critical memory accesses are critical. So whenever something is not one cycle, you have like a huge, penalty. Okay, I think we need a break. I think we're moving quite slow today, but I'm fine. Whatever slide deck I have at the end, it will be all shared with you, right? So whatever I won't be able to cover, you can read on your own, right? But I make sure that we cover the most important things. Let's have a 10 minutes break now. So see you at 2:15. Okay, I hope everyone is back from the break. As usual, please turn on your cameras if possible. We'll continue. Okay, so I hope I introduced the need for caches and spatial temporal locality is clear for everyone. The next problem we have to deal with, and it's the problem appeared from the beginning when the caches were introduced and stays for up to this day because the answer is still might be different, is whether they want to manage those new hardware resources manually or automatically. So manually, programmer manages data movement across all the levels, right? And the downside is obvious. It's very painful for programmers on substantially large programs to do manage caches themselves. So it's still done though in some embedded processors and in GPUs. So GPUs specifically, when you know what the kernel is doing, it's so important that you can dedicate optimizations for that. They had a so-called shared memory, right? A scratchpad memory where you can fully manage everything yourself. So it gives you some room. So it's not a dumb idea as you might think, right? So people still do it. Automatic clearly makes programmers' life easier. The average programmer doesn't need to know about it. You essentially don't need to know how the cache works right now to write a correct program. But is it going to be fast? Well, it depends. If you're lucky, it might, and the system figures out if you're going to write something crazy in terms of code, it might not. So the replacement policy is automatically never as good as the one written manually. Okay, so how does the modern memory hierarchy looks like? From the very, very top, we had a register file. Remember, this is somewhat outdated numbers, but still representative. Then suddenly a second granularity for register file. Then we had L1 cache that use exactly the same technology. So remember, register file versus L1 cache. Sometimes students get confused and they think register file is built out of something else, right? That's why it's faster. No, the reason why it's faster because it's smaller, right? So accessing it's easier, right? L1 cache literally built from the same granularity. If you're not sure about it, one good proof of it is the fact that modern GPUs, chips, allow you to transfer a lot of their registers they have into memory, like L2 cache, and vice versa. So if it would be a different technology, it would be quite different. So they really allow you to automatically decide how many registers you want versus how much cache you want to use. Okay, so L1 caches, L2 caches on the order of megabytes. So L2 caches tend to be shared in many cases, but not shared across all cores, right? They're shared across a few cores, and L3 cache usually shared across everything. And then you had main memory, then you potentially had, non-volatile memory DIMMs and SSDs, and then disk. Okay, so how does this work? I'll just show you relatively quickly one example on how the game of averaging works, like why with the smaller piece really helps. So essentially, we're going to get numbers from not such a hypothetical architecture from one of the Pentium 4 chips from Intel. So essentially, for a given memory hierarchy level I, it has a technology intrinsic access time of TY. When I say technology intrinsic, it's not just about it, whether it's SRAM, SDRAM, but it's also about its size. But that's the technology driven, but there is a perceived access time, something how it looks like it works for you. So if I had something big and I put something small in front, it's not that the small TOI dictates, it's the perceived time that is important. So except for the outermost hierarchy when looking for a given address is we assume there is a chance to get a hit, which we call the hit rate of HI and access time of TI. And there is also a chance of miss, which we're going to call MI, that you miss, and then your access latency becomes the current layer plus the next perceived layer. So essentially, if you hit the current layer, your latency is TI. If you missed in it, then your latency becomes the perceived the next one. It means that it's not necessarily small TI plus 1. It might be something better than that, right? Or worse than that. And HI plus MI, obviously it's hit plus miss. The total is 1, right? That the total probability is 1. So what we're going to get this here, and it's relatively straightforward math. There's no like rocket science here. So the perceived TI is essentially the probability of a hit in this layer multiplied by the access latency of that layer. That's how people were going to see your layer if you're going to hit in it, or a miss rate multiplied by TI plus capital TI plus 1 from the latency from the next layer. And essentially, if you simplify this out, that's what you're going to get. So essentially, this is the math behind how the perceived time changes over time. And essentially, as you look at it, you're going to see that's a recursive latency equation, right? So TI depends on TI plus 1. So the goal is to achieve the desired T1 within allowed cost, because what we care about is how the core, which is at the T1 level, sees the latency of the whole memory hierarchy. And the best you can get as you look at this equation is to come as close as possible to T small I, because you cannot beat that, right? But obviously, depending on the miss rate and the perceived latency, things might get worse than that. So that's your goal. So how can you get it? Well, if you look at these equations, things look somewhat trivial, but they're not easy to achieve. So one is keeping the miss rate low. Keeping miss rate low, it means my layer, like a cache or memory, needs to get a high hit rate to make MI low, which means I can increase capacity, right? But if you're going to increase capacity of the layer, that's going to increase TI itself, right? Because the latency of that layer becomes worse, right? It becomes larger, so it becomes slower. Or you can try to reduce MI by doing some smarter management. So replacement, so trying to anticipate what you need and store the things that are more critical, or prefetching, try to anticipate what you will need, right? So essentially replacement and prefetching helps us to do smarter decisions and management, so to reduce their miss rate. And obviously, you can also try to keep TI plus 1 low. So it means you try to build faster, lower memory hierarchies, but that comes with increasing cost, and introduce more intermediate steps as a compromise. So let's look at one example. That's a P4 90 nanometer chip that runs at 3.4 gigahertz. That's what it has back then. L1 data cache with their size of that L1D cache was 16 kilobyte. And that's not that much different from modern chips that might have like 64 kilobyte L1 cache. And the latency of that essentially cache were 4 cycles for integers and 9 cycles for floating point. There was also L2D cache that was 1 megabyte in capacity, and it has 18 cycles access latency in that level. And there was a main memory where the access latency was 15 nanoseconds, or roughly 180 cycles. So, so notice that the base case latency here is not 1, right? And the worst case latency can be as high as 500 cycles. So let's do the math. So let's look at one possible scenario. So if miss rate at the L1 level is 10%, and at the L2 level it's also 10%, then if you do the math with the numbers we have, you're going to get T1 at 7.6 cycles and T2 at 36 cycles, right? That you're going to get, just trust me, but don't need to do the math for you right now. If you are magically able to reduce the miss rate by 10x, right? What you're going to get is your latency on the first level is going to reduce by close to 2x, and so is on the T2. And that's actually not unrealistic to get hit rate on the 99%. But if you see that if you go between 5% and 1% on the first layer cache, then the latency goes just from 4.2 to 5.20, right? You see, so that there's a diminishing return in terms of miss rate, right? So the latency didn't change as dramatically. But if you're gonna change M2 to be like 50%, then the T2 becomes like 100 cycles, and that does affect T1 a lot. Okay, so this is the game you can play to see how different parameters affect the design of a cache, and that's what architects do when they design the memory hierarchies. Okay, so let's go and talk. Yeah, Pavel. Pavel, you're muted.
Sorry. when it accesses different layers of cache, does it access L1 first, and if it's not an L1, it looks in L2? Does it?
Yeah.
Or
who knows that? Who knows the answer?
Yes.
Mustafa, you know the answer?
Yes, I'm guessing, because like the
right, because we're adding T1 plus the miss rate, right?
Go back
other.
to that thing in adding.
So in this case, we assume that, but it's not a requirement. So you can do certain things speculatively.
Right. I was wondering, are there any like architectures where it tries to access multiple levels at the same time and send back the short, like where the closest?
Sometimes it's possible, but it's not the most common because it complicates management and coherence.
Okay.
But it is possible.
Another question for cache access. I was just thinking now, is it the decoding the address itself that takes time, or is it like the distance on a two-dimensional die? So like, will 3D stacking help with memory technology?
Neither of the two is the most critical bottleneck, although they all add up to the latency the most. We're going to talk about cache organization soon, so you're going to see where the bottleneck is. But the short answer is figuring out where it's located is the most time-consuming process. It's not about searching on the 2D die. It has certain organization with associativity and everything.
Gennady, could you repeat the last 20 seconds you interrupted?
Okay. So what I was saying is that there is a certain organization, the way the cache built to be manipulated efficiently, and dealing with that organization takes time. So you're not dealing with the raw 2D organization. You had sets and ways, and that's where it gets more complicated.
Right.
Essentially, not reading from it is definitely adds up to the latency, but the problem is if you had something really large, how are you going to quickly find where the data you need is located? It's like looking for a book on a shelf. That takes time. So when you know where the book is located on the shelf, grabbing it, it might take time, but it's not as bad as searching for the book on the shelf. So searching on the book on the shelf is the most time-consuming process. And if you make it too parallel, you lose a lot of power. Okay. Mustafa, did you have any questions?
No, I just looked at the slides and figured it out.
Okay. Okay. So essentially the cache, informal definition is any structure that memorizes frequently used results to avoid repeating the long latency operations. For example, web cache has the same property. Most commonly in the on-die context, we are talking about automatically managed memory hierarchy based on SRAM. That's what the typical caches are, but it doesn't have to be like that. So caching basics. So what cache consists of is the blocks. So the all called lines of the cache or cache lines, units of the storage in the cache. And there are some exceptions, but usually this is uniform. So there's usually some uniform size you pick. Memory is logically divided into cache blocks that map to locations in the cache. So essentially, the whole memory is huge, cache is small. You cannot have everything in the cache at the same time, but we want to know if we had this address, where it would be located in the cache. Then on a reference, you can have two scenarios. You can get a hit. If in cache, you use cache data instead of accessing memory. If a miss and it's not a cache, you bring block into the cache. So that's how it looks from the cache perspective. You either find the data in there or you missed, then you need to bring in something in the cache. Probably you need to evict something from the cache to get space as well in most cases. Some important cache design decisions: placement, when, how to place and find blocks in the cache. That's one of the most important. That's all calls cache management. Replacement, what data to remove to make room in the cache. Granularity of management. Do you manage everything at the block granularity, line granularity, or the larger chunks to save on, circuitry on power? Write policy. What do we do about writes? So there are multiple different scenarios you can think about, right? It can be write through, you can write a lock. We're going to learn all about that. You might write immediately, or you can delay the writes, right? So all this portion, because writes are not on the critical path compared to reads. And instructions data. So do we treat them separately? Do we treat instructions different from the actual data, or we treat them uniformly? Okay, so what is the cache abstraction and metrics here? So as Pavel mentioned already, there is obviously an address coming there. And where the complication is that a lot of students that never work on caches, they always think about cache as being just a data store, right? So the data is stored somewhere, right? The problem is, yes, it's mostly the data, but I also need to have an index to find things on this data, right? I need a bookshelf index like in the library. So that's called text store. So it tells us whether the address is in the cache or not, and it has some bookkeeping information on how to remove blocks. So the text store, when we access, tells us hit or miss. So, and essentially the cache hit rate is defined as the number of hits divided by the total number of accesses. And the average memory access time, called AMAT, is used as one of the primary metric for accessing the cache. So the perceived time from accessing the cache is, again, hit rate multiplied by the hit latency, which plus miss rate multiplied by miss latency. This is the average access time you get from the cache. And a basic hardware cache design, we will start with it first. Then we examine a multitude of ideas to make it better, which I probably won't be able to cover everything today. So blocks and addressing in the cache. So memory, as I said, is logically divided into fixed size blocks. Each block maps to a location in the cache determined by the index bit in the address. So this is a very straightforward implementation, really. So we use the index into the tag and the data stores to find it. So for example, if I had an 8-bit address, I can have 2 bits for the tags, 3 bits for the index, and then the offset within the bytes in the block. And when you had a cache access, it essentially takes the bits it needs from the address that you search for, and it uses these bits to quickly find your answer, whether this data is stored in the cache or not, right? Then you check validity bits, and then you compare tag bits. And then if a block is in the cache, then the stored tag should be valid and match the tag of the block, right? So it's essentially the way you do, you have data request coming, for example, read, it has a tag on it, right? You matches it with the tag in the data, tag match, then you can have it, right? If not, then you would issue a request down the stack to the low level cache hierarchies or to the memory, right? And then it will arrive and update the tag, right? And validate something. So the tag needs to be always valid. So there's a valid bit on the cache. Okay, the most simple and trivial.
So just to make sure, the tag inside the address, what does that contain? Is it just to any bits or?
Let's wait a little bit. You're gonna see it in precise examples,
okay.
Right? Certain bits of the address interpreted as a tag bits. Like when you're gonna see how we organize it, you will understand what needs to be there. So the first, the easiest caches to deal with are called direct map caches. So essentially you assume that, like for simplicity, we assume that everything is byte addressable, and we had 256 bytes and 8-byte blocks. So 8 byte is the size of the block. Then we're gonna have 32 blocks. So then your cache is organized this way, right? And if you had 64 bytes and 8 blocks, then in the direct map cache, essentially each block can only go into one location, right? So it means that if you know the address, there is a way to take the bits of the address and you know the exact location. So what's gonna happen is you have a data store and text store. And what's gonna happen, you're gonna take the index bits from here, from the address, and that's gonna tell you what your tag is, right? Should be your tag here. And you're gonna look at the tag bits that exist in your address. And then we're gonna do a tag matching, right? So essentially based on the index bit of your address, there is only one location that the data corresponding to that might be stored, right? So when you arrive to the shelf, think about it this way, the best way to think about it without thinking about the math first. You're coming to the library and you're saying, I want a book with this author name, right? So it knows that the name tells you the shelf. You go there and there you look at your tag of your title with the tag there, and then you do the match, right? You know it can only be on that shelf, right? But the fact that it can be on the shelf doesn't guarantee that it was there, right? So it might be taken by someone else, right? You come and check, and it happens to be there, tags match, that's what you do, okay? We will work out all the low-level details about that, but that's conceptually the analogy, right? So the fact that, so you always want to know where it's located, so you don't want to need to search the whole library, right, for the book. But the fact that it can be on this shelf doesn't guarantee it is there. It might be there if someone recently put it there or not. Okay, Mustafa?
So my question is that we're only using the index and the tag bits. What about the other 3 bits in the address? Because that means that like there's 8 possible addresses that would match the index and the tag, right?
Yeah, we're gonna break essentially. It's a very simple concept if you think about it. If you know that, say, your cache has only 8 blocks, so you take the address and essentially you start from address 0 from your memory and through address n. So the first 8 byte can go to the first block, the second to the second block, the third to the third, and then you do round right after 8. That's it. So you only need a few bits of information because that's the only bits you use to store the data. You just need to be a little bit patient. You're going to see more details on that. But essentially, if you only had 8 shelves, right, everything should go on one of the 8 shelves, right? So you just come up with an easy strategy on how you map it to these 8 different shelves. Does it make sense, Mustafa?
Kind of, yeah. So
yeah, so it's essentially if your hash only had 8 blocks as in these examples. So that means in your address, you just take the address, do mod, like divide it by 8, and the remainder will tell you where essentially the address would be. So you just need 3 bits of your address to know where it's going to be located. Okay, so and then you check whether it was really stored there or not. And then you had maxes that will give you the data. So addresses with same index content for the same location. Obviously, it can create conflicts, and that's a big flag of caches, conflict misses, right? So direct matches is the easiest possible organization. Everything has just one possible location in the cache, so you literally know where to search for it. Search is fast, but if you're unlucky and you have a very small cache and you had, say, 2 arrays, and they happen to be aligned. So if you read array A 0 and then array B 0, so each of them are going to kick out each other, right, on each axis. So you cannot really benefit from caches because of that. We're going to talk about that. So essentially direct map caches, 2 blocks in memory that map to the same index. And I'm trying to realize to that you say they just do div by 8 or something if you had 8 blocks. In reality, it's more complicated than that. But the key thing is there's a certain number of index bits from your address. You can always perfectly identify to which part of the cache you need to go and look for, right? In the direct maps caches. It might use some hashing function, but it's all complications which we don't need to go into right now, right? So essentially 1 index means 1 entry. That's the key idea of direct map caches. So is this part clear? I guess Mustafa still has a raising hand. I'm still not sure about it.
No. I was just confused because I forgot that the cache line has 8 values. So like it has 8 addresses in there. I figured it out.
Yeah. So the best way to think about it is like, again, library is a good example of thinking about the caches, right? Like you arrive there and by the name, you know which shelf to look at, right? And it might be that your book can be only on 1 shelf, but in a more complicated library, it may actually be on several different shelves. And we're going to talk about this next, essentially. So what the problem is, if you had 1 index, 1 entry, if you're unlucky and your program is written in a way where 2 frequently accessed things are located on have the same index, right? They're going to kick each other all the time. So this is supposed to be a quick question for you, but I'll just show you the answer. So direct map caches fundamentally can lead to a 0 hit rate if more than 1 block access in an interleaved manner map to the same index. So for example, if you have something like AB, 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 and each of them has the same cache index, you're always going to have a conflict miss. So you always have whatever you want to have there. If you want A, you have B there. Then you kick out B, put A there, and so on, right? So you never get any benefit of the cache. So even though the direct map caches are the easiest to build, right, and easier to manipulate, they are relatively infrequently used. So you're not going to see them in your laptop. Even L1 big cache is going to have at least two-way associativity, which we're going to define now. So what is the associativity? Associativity is a feature of the cache organization that allows to break those conflicts. So if the address 0 and 8 always conflict in direct map caches, we try, give them some flexibility, not let there's only one thing that if you're in this index, you can only one slot for you, increase the number of slots. So essentially what's going to happen is that your tags are not going to be just one monolithic structure. It's going to consist of a sets. And the data store is going to be done the same way. So you split it, and whenever you're going to search for an item, it can be located in either of the two big columns, right? So that means if I had this, pathological situation when one thing kicks another thing, I don't have to, I'm not limited by having only one of them at a time. I might have both of them at the same time, right? As you can see, it is not for free, right? I would need to now match not a single tag, but two tags. And if you want to cut the latency, I need to do this in parallel. If I do it sequential, which is possible that my latency goes up. If I do it parallel, then it becomes more complicated. I would need to use more logic to do it in parallel, and it also increases power. So anyway, but if I do that one way or another, the key is that the maxis is going to give me actually both data points, and then I would need to select the bytes I need. So the key idea here, having associative memory within a set, right, to deal with this problem. That's the idea. Most of your caches right now are set associative, and the granularity of associativity can vary. You can have two ways, meaning you have two columns like that. You might have 4, you might have 8, you might have 16, and so on, up to 32. That's what I've seen so far. And the idea is to specifically deal with conflict misses. Okay, so high associativity. So I talk about 4-way caches. That's how it's going to look like. As you can imagine, things get complicated very quickly, right? So but I wanted to make my cache efficient. So likelihood of conflict misses becomes even lower, but you need even more tag comparators and wider data maxes and larger tags. If you think about an extreme going from direct map caches, another end of the extreme is a fully associative cache. It means that a block can be placed in any cache location, right? So it's completely flexible, right? So how that's going to look like? Well, it's going to look like crazy like that, but it's not infeasible, especially for small caches. They can be fully associative. Obviously, associativity brings the trade-offs. As you probably notice, the degree of associativity allows us to reduce the conflicts. But the question is, how many blocks can map to the same index or set? The high associativity, you get high hit rate. But as you might think about it from the conceptual perspective of how you write the code, then probably the high associativity I have, the net benefit of reducing the conflicts goes down. So going from direct map to two-way, I remove a lot of conflicts, but as I get more high and high associativity, I keep paying the higher and higher cost for a smaller and smaller benefit. And that's the job of an architect, to figure out for a generic set of applications what's a good trade-off. So essentially you get high hit rate, but you get slow access time, right? Because you either need to handle some of the stacks sequentially or in parallel. And it's more expensive hardware, but requires more comparators. And there are obviously diminishing returns from high associativity. The typical curve, if you plot associativity versus hit rate, is like that. It saturates relatively fast. So this is why you don't see designs beyond like associativity of 16, right? So somewhere between 2 and 16, that's what you're going to see. And it's also going to depend on the layer of the cache. So the L1 cache, they tend to be two-way or four-way associative. They only resolve the basic misses, right? But the deeper shared caches, they may have way more misses. So the question for you, why is that the case? Why the shared L3 cache tend to be designed with much higher associativity than L1, individual caches per core caches. So why do you think your L3 on your laptop probably going to be 16-way associative, while your L1 data cache is probably 2-way or 4-way?
Also,
Jimmy was first. Sorry, Mustafa. Yeah, but mute yourself, Jimmy.
Sorry, so the L3 is shared between multiple cores, which means there's going to be the memory accesses across different cores should have less spatial locality.
Yeah.
So there's less points in, yeah.
You're absolutely correct. So essentially, the more cores, the more active contexts, the more different computations and loads and stores happens quite independent. There's a high probability they're going to conflict, right? If you had say 16 core machine and it has hyper-threading support, at least 2, it means you can have 32 independent threads running, right? So they can thrash things quite a bit. So people want to make sure there is at least pathological cases are not happening, because things tend to be aligned nicely. If you had arrays in all of them and run the same versions of the same application, there is high likelihood that every beginning of the array are nicely aligned. They all start to hit in the same thing, right? So you tend to make sure that your associativity at least avoids the basic conflicts, right? And that's not needed in the L1 data cache, where you don't have that many streams, okay? Okay, so what are the, so I guess Mustafa, I probably have the same answer, right? Didn't you?
I was gonna more point out and say that, like, I guess from L3 to DRAM, like going there would take much longer, so it might be more feasible to give up a little bit of access latency for a higher hit rate in L3.
Yeah, it's true, but I mean the first argument that Jimmy mentioned, it's more of an important thing. So that the problem that associativity goes up, it's mostly about how many consumers you have. So think about it as, at a restaurant, you only have that many plates, that's your throughput, right? You have that many parallel contexts. So even if each context has at least one stream of instructions, right, generating memory accesses, that's already like 16 contexts, right?
Yeah.
Okay, so what are the issues in the set associativity caches? So each block has to have its own priority, indicating how important it is to keep the block in the cache. But the problem is, and it's still a problem to this day, despite several hundred of papers published on the topic, is how to figure out the priorities between the block. There are 3 key decisions you need to make. They're called insertion, promotion, and eviction. And eviction is also called replacement. So insertion is, what do I do in terms of priority on a cache field? Why do I need priority? Because when I had set associative caches, if I had, say, 8-way associative cache, and it means whenever I need to take out something from one of these 8, I need to decide which one. And I need to be smart about that decision. I want to remove the one that has the least chance to be reused in the future. But how to do it without knowing future in advance? It's difficult. So essentially caches implement some priorities, which are essentially heuristics that tend to work in general, but not always. And to figure out those management policies, you need to figure out 3 big parts. So how do I set up my priority? So when I see the block from the beginning, where do I place it? At the tail of the priority, at the top, in the middle, right? All this is a question. So another question is promotion. So obviously, if you're just going to place it in one priority and never move it, it's not going to really help you. So what you want to do is when, say, that blocks get a new hit, you say, you know what, you already hit it a couple of times, they're probably going to promote you to a higher priority. You're probably an important block. And if you don't get hits for a long time, I want to depromote you, right? So that's a promotion policies. How to figure it out, again, with some simple logic that can be done in the cache, it's not trivial questions. Whether and how to change the block priority, that's promotion thing. And then eviction replacement. What happens to priorities on a cache miss? So if something misses, how do I update it? Okay, so eviction replacement is an important thing. That was such a hot topic for so long time. So in computer architecture field right now, it's getting almost impossible to publish anything in that area. It's not because it's not interesting anymore, but it's mostly that there are so many ideas people try out. So it's like, it's similar to like last Fermat theorem, right? Proofs, right? So it's like, it's just too many people tried and they get there, some results on that problem, but it's like very rare that you go for that. It's essentially, if you submit a paper on this topic, most of the reviews going to tell you that you're working on an incremental topic, no matter how radical your solution is. So people are tired of the topic, essentially, right? It's one of those topics that people work really a lot. So, so which block is the set to replace? It's something you're trying to figure out. If something is invalid, and the question is for you, how is this possible that the cache can be invalid? Like a cache block can be invalid. So what are the scenarios that can make a block? Like why we don't even have validity bit, like valid or invalid? How is it possible? Like there are two big scenarios. I want to hear from you when this happens. Right. Try to think.
Well, so I guess one would be that, let's say you have two threads working on something. One of them pulls something into cache. Then the other one needs to pull something into cache, so the original one gets replaced. So then, like when the first one tries to access it again, like it might still think it's in cache, but it's actually invalid.
Yes, that's correct. First use case, but that's a more harder one, but there is a simpler one.
There's also what's called a code miss, which is where
Yes.
Maybe your machine just turned on and there's nothing in memory.
Yeah, at the beginning, remember, like at some point I turned on the machine and nothing was yet in the memory. So there's nothing really there. So I need to kind of tell that there's nothing there. That's why I set validity bits to 0, right? Initialization. That happens when you turn on the machine, also when you can want to flush the cache. Sometimes between, say you had a cloud, right? And you run something there, you don't want to have something in the cache from the previous user, right? So you want to do some cache flush, right? So when you do cache flush, you invalidate the blocks, right? So this is the two real scenarios. One called misses, or like the data that was not supposed to be there, or you're not supposed to see it. And another one, some form of sharing, right? When there are two different versions of the data and one might have a stale version of it. So you have to invalidate it. Okay. If something is invalid, you just take it. If all are valid, which is the most common case, then you need to consult the replacement policies. What kind of replacement policy can be random? And you might be surprised it's not such a dumb policy. Actually, it might actually help sometimes. I've seen several proposed policies in papers in computer architecture field that works worse than random. So random is expensive, unfortunately, right? True random is expensive. First in, first out, then least recently used policy, and implementation is not trivial as you may think about. Not most recently used, least frequently used. All these options were considered, and there's the list of things possible here is humongous. So we're not going to talk too much about this. There's also hybrid policies. They use a lot of different techniques. The bottom line, this is heuristics, and people like heuristics and hate heuristics for two reasons. They like them because you can infinitely, incrementally build in this area. You can keep publishing more and more because you just keep coming to new heuristics, and you can always argue that one is better than another. And they hate them because if you're the person who has to design these things, that's the worst possible thing, like having tons of heuristics in your chip. So, but that's what happens with replacement. You should understand it's always heuristics, right? But some of them are better than others. Optimal replacement policy. So anyone knows the optimal replacement policies and how it's called? If you take a computer architecture class.
It's like, I don't remember, I think Omega or something like that, when you know the future.
Yeah, it's called Bellad's optimal policy. So if you know the perfect future, you can literally allocate that. That's called Bellad's optimal. Yeah. I remember one of my small contribution to this area where I showed that if you use cache compression and your blocks are variable size, that they're generally considered optimal policies. Bellad's optimal policy that ignores the sizes actually not optimal anymore. So people always use this as a reference, right? But if you start to compress blocks and you don't store information about it in the cache, your optimal policy is not optimal anymore. This is something I showed in one of my papers. So it's not super intuitive, but when you're going to read the cache compression paper for the next class, you're going to see this, right? Okay, it's the placement policy was not in this paper, in the follow-up paper, but you're going to see how the problem might arise when the sizes of the blocks change. So implementing LRU, LRU stands for least recently used. It's one of the most common used policies, although the fully real LRU is not possible, and then leave the questions for you on why it's not easy to do. So I just leave this few questions in the interest of time because we had just 5 minutes left. And essentially, instead of real true LRU policy or perfect LRU, people use some approximations. And that was used for a long time by Intel, even though Intel never officially announced which replacement policy they use, but you can reverse engineer that by, having known pattern and, figuring out how the latency changes depending on what you run. So people do this reverse engineering. Yeah, so the people come up with a lot of approximation. I think that the most, if you want to know what is the most state-of-the-art replacement policy that are really using real chips, it's called reference interval predictions, or RRIP. So there is a paper at ISCO conference about 10 years ago. If you're really curious about the state of the art, this is roughly what Intel is doing right now. I believe IBM as well, right? They're not going to admit it, but just if you're curious about what happens, that's roughly what they're doing. Okay. Okay, so that's replacement policies. Then it can be hierarchical. I'll skip over that because it's not as important. I want to touch on other interesting things. So the optimal, that's what I mentioned to you, valid is optimals. You replace the block that is going to be referenced furthest in the future by the program. So this is your optimal. So like if I know perfectly the sequence of blocks that come in the future, what would I do? And that was introduced in 1966 by another guy, Belody from IBM. How do you implement, simulate that? That's the questions that have, like if you're a computer architecture researcher, that's something that you might look as the best possible for the optimal. Okay, so I think, because I had only 3 minutes left and I don't want to delay you guys. So I'm gonna share the slides. I'm gonna stop more or less here, and then I'm gonna continue in the next lecture from here. Let me just context switch and show you a few last slides that would show you, we need to discuss your reviews. Yeah. Yeah. So so this is just where are you guys? You can see the slides, right? Again. Okay. So I want to spend a few minutes to comment on your paper reviews. So again, I think I mentioned it briefly, but I'll repeat it again. Most people figure out it the right way, although I would have to say that we were very generous in the first review, so you can keep learning. Even if you get a nearly perfect score or a perfect score, you might still get some feedback from a TA if something was not great, but he just didn't want to deduct the scores. Content and merits are usually summarized well. It's over many years of doing this class. I already figured out that's easy for students. The main problem happens in the weaknesses and future work parts, as you can imagine, because this is weaknesses that tend to be hidden, especially in good places, and future works, that's where you need to be creative. Creativity is always hard. So some feedback from the review one is some people were too focused on non-technical things like writing quality. Don't get me wrong, writing quality is very important, but we want to focus on technical merits, not about how nicely paper is written. And most of the papers that were given to you would be actually well written, so that's not a surprise. So that's not what we want to hear from you. Having no future plan is actually not a weakness, right? There are many reasons why it will happen. First of all, some people don't like to submit papers with future plans because they might lose on the ideas. There's a competition in the area. That's one reason. Another reason, you write like future plans or your own weaknesses in your paper, well, reviewers are going to just copy paste your stuff in their review and said, well, go figure it out, right? And then we'll talk next time. So there is a tendency not to talk too much about your future. And the third reason is more pragmatic space, right? Like you want to talk about a lot of things in your paper and the space is limited, right? So you don't have an infinite space. So it's not the same as archive. And another thing, remember from the first lecture, numbers is less important. Don't cite their, precise percentages of speed ups of different things. That's not the most important. The most important thing is insight ideas. Focus on that, right? The numbers are just to back up those claims. Okay. I think your grades are shared with you. We use last 4 digits of your student ID as the hash, so you can see roughly how others are doing, but at the same time, we don't tell everyone how other people are doing specifically. This is the grade distribution. I think the people who got 6 and 8 probably want to talk to TA if you're not sure what you did wrong, right? Okay, then this is just review number 3 is going to be my BDI paper. Hopefully to hear some interesting feedback on that one. Okay, and I think we're out of time. So the people that want to have a meeting with me to discuss the project today, could you please put your names in here and your email addresses? So, and actually, no need for email addresses. I just want to get a rough head count, how many people needs to talk. So just set in the chat so I know through the send the link. If there is at least at least a couple of people, then I would send the link to people that needs that to meet after the meeting, and that won't be recorded. Okay, don't see anyone so far. So if, yeah, Jimmy?
A question. So I'm part of a group, like we might want to discuss ideas because we don't really have project ideas. Is that something that
Well,
is
if you
amenable?
form a group and you're not completely lost and you're looking for a topic, then you can still look for it, because there is a downside to talking for me from the beginning, because I'm going to probably influence your project too much with my bias. So keep searching for the ideas of your own. Then later on, if you're not sure, you want to bring some ideas and get my opinion, then let's do it. So.
Okay. And will we get feedback on the, I guess is the quality of the idea being proposed?
Yeah. So you can come and like you can say like, I want to try blah, 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 and say like, you know what, I'm not an expert, but it feels like that was done before. And then you might revise what you're trying to do.
Okay.
I can also comment on the potential. So we can do it, but I still I'm right now more focusing on the people that cannot form a team or completely lost. Especially remember we had a couple of undergrads, so we need to help them. So if they need help and they were not able to form a team so far, they are the top priority, right? Remember, even the proposal stage is not final. You can still keep changing things afterwards. Okay. So I don't see anyone in the chat so far. Did I miss someone? Because if that's the case, then I guess we would be done for today.
I think Alex said that both of us want to talk.
Who said that?
Alex.
I did.
So we're working together.
Oh, sorry. Maybe something wrong with
Also somebody else mentioned they want to talk to you in the chat.
Oh, I see. Yeah, I see. So Alex, sorry, the chat was not showing up properly. Yeah. So Alex and Mustafa and Kirkan Park. Okay. So I think that's it. So what I'm going to do right now, I'm going to stop sharing. I'm going to post a Zoom link here, separate Zoom link to Meet, right? And the people that are interested, please join, and I will put you in the breakout rooms, right? And then we'll meet. Sounds good? Okay.
See you.
Yes.
Bye.
Bye-bye.
Thank you, guys. So others, please wait until I give you a link. Okay, so guys, that's the link to use for people that need my help. And those people, I guess, Alex, Mustafa, and Kyokun, I'm going to see you soon, and others have a nice day. And yeah, good luck with the project. Thank you.